going to be the sequence. So first, before I start, I would really appreciate if this session is interactive. So there'll be some instead of me giving some talk I want it to be a two-way communication, not just me talking something. So there'll be some questions. It will be great if some of you can volunteer to answer them. Okay, so it'll be fun, and please don't feel shy or hesitate. Feel bad about making mistakes, because if we don't make mistakes, we never learn. So don't feel shy about making mistakes, and please try to volunteer to answer. Okay. So it'll be like small puzzles like things, so that you will also be engaged. Okay. Okay. So and you all learnt about register allocation, right? Register allocation, data flow analysis, basic block scheduling, right? It is all of them will be used or will be related to what I'm going to talk today. Okay, for instance, you learned about basic block scheduling, and this is this talk will go beyond basic block scheduling. Why do we need global instruction scheduling, and what are the challenges posed by embedded applications? And this talk also will cover a bit about the implementation details in a real compiler, and then we'll highlight the results and conclude with what can be done to improve this work. Okay. Okay. So okay. Why do we need global instruction scheduling? So before that, I will tell what global instruction scheduling is. Today, we in the morning we saw about scheduling within a basic block, right? Can you tell me what a basic block is? Yes, exactly right. So it's a sequence of instructions where you cannot, there is a unique entry point and there is a unique exit point. You cannot control cannot enter in between the instructions. The control can enter, we can enter only through the entry point, not anywhere between. Okay, so yeah, that's a basic block, and we saw how we can okay, why do we need instruction scheduling? Why do we want to why do we want to reorder instructions? Yes. Right. So if a long latency instruction executes, and in the program order there is an instruction that immediately uses that value that is being produced by the long latency instruction, then the consumer has to wait till the producer produces its makes its result available, right? Till that time there will be a stall, as you said. Your name? Aditya, as Aditya said, right? So we don't want to spend our time idle, right? So we don't want the process to be idle during that time. So if we can bring in some other instruction that is not dependent, that will not use the result that is produced by the long latency instruction, then we can make better use of the things, right? So yeah, that's one of the main motivations. Performance is one of the main motivations of instruction scheduling. And yes, in basic block scheduling, what we do, we reorder instructions within a basic block, right? Okay, so yes, okay, and why do we want to go beyond basic blocks? Because this is a fact. load instructions are some of the, one of the biggest culprits of, I would say they are you know that memory is a lot slower than the process CPU, right? That's why we have caches. But even the L1 cache, right? Even the L1 cache may take a couple of cycles to produce the result. If you want to read from L1 cache, in some processes it may take 2-3 cycles for the result to be available. So this one, load latency is one of the main reasons for performance degradation in many processes, particularly if you look at embedded process or like that. And you also learnt about branch penalty, right? Yeah, I hope you are all familiar with instruction pipelines, right? So what is a branch penalty? Why do we care about branches? Why are they special?
Modern cluster it will be like around 8 stages, so you have to flush out the entire pipeline. So it will be like already like you'll be wasting around like hundreds of cycles by the time.
Right. Yeah, it depends on when you resolve the branch direction, right? By the time it may not, for a branch instruction, it may not be. Yeah, maybe a couple of cycles we may have to waste if right, if the prediction was incorrect, right? And some process may not even have a branch prediction unit. Okay, so. For instance, embedded processors may or may not have sophisticated branch predictors. So if we have to take a branch, it will take some. We'll have to lose some cycles. So yeah, this is just a fact I am stating. Okay. And if we have very small basic blocks, 1 or 2 instructions, right, then we can't do much, right? We don't have many instructions to hide the latency of the long latency instructions, right? So these two are the main main reasons why we may have to go beyond basic block scheduling. If we have very small basic blocks, then that means that we don't have much, the scheduler may not have many instructions to hide the latency of the long, latency instruction, right? And if we have small basic blocks and the basic block terminates with a branch taken, if you have to jump to a different location, then after executing the instructions in the small basic block, we have to pay the branch penalty, right? So that's why we need to go beyond. We need to think about scheduling beyond basic blocks, right? That's where global instruction scheduling comes. In global instruction scheduling, you will try to move instructions from different basic blocks to achieve performance, to hide latency. Okay. So yes, so this will allow global instruction scheduling enables movement across basic blocks, so that even if a basic block is smaller, right, if you can bring in an instruction from another basic block, then there is an increased chance of hiding the latency, right? Yes, and there are many global instruction scheduling techniques, and in this session the focus will be on what is called trace and superblock scheduling. To motivate you, this is an instruction sequence. Okay, can you tell me? Can you guess what is the? Can you tell me the length of the basic block starting from this instruction? Huh? One. Why is that? Yes, branch, but this is an exit, right? There is an entry, and this is also part of this basic block. This is actually there are two. The length of the basic block is 2, right? So, and if you can see this, we are loading into this register R0, okay, and we are immediately reading from R0. So if the load latency is 2 cycles, I mean, then there'll be a 1 cycle stall, right? You see this? Yeah. So okay, and this is a label, and can you tell me what is the basic block starting from this, length of the basic block starting from this instruction? Assume that this is only one instruction. What is the length? 1 or 2? Why? Okay, who said 1? Can you justify why it's 1? Yes. Yes, Aditya, yeah, go ahead. Yes, yes. I am saying this is a label. This is not an instruction. Okay, so this is a label. Okay, this refers to this address, the address of the unrelated computation. This instruction. Can you tell me what is the length of the basic block starting from this? Why is that?
Because when we create basic blocks, we have the rules like if the program starts, then that is we mark that as reader, or also the labels also we mark as readers. New label starting on the next.
Excellent. Yes. So the rule is there is only one entry, right? There is only one entry for the basic block, right? So if we have this, right, there is a potential that, I mean, there is a label because there is a possibility of control flow entering this one label, right? That's why it's just one instruction. I mean, control can reach from some other somewhere else to here. That's why this label is here, right? That's why the length of the basic block is just 1. So if you can see this, right, I mean, there is not much the basic block scheduler can do to hide latency of this load, right? There is nothing to choose. There is only one choice, and we have to schedule this instruction, right? So you can see that, I mean, if we can schedule instructions across basic blocks, it'll help, right? So yeah, so this is just a motivation for global instruction scheduling. So I'll give you an overview of global instruction scheduling. Okay, so what is this? The picture here? Yes, control flow graph, right? What are these nodes? Basic blocks. And what are these edges? Okay, what do you mean by that? If there is an edge from BB0 to BB1, then what does it mean? Yes, there is a possibility of control getting transferred from BB0 to BB1, right? Okay, you can see that some edges have labels, right? Okay, I'll tell you what these labels are. Okay, these labels indicate how frequently an edge is taken. Okay, for instance, this basic block, right, BB1 has how many successors does it have? What are they? Right, BB3 and BB2. So it means that from BB1, it's equally, I mean, any of the BB3 and BB2 are equally likely to be taken, right? Can you give me a skewed edge? This is 50-50, right? Can you give me a very skewed edge? Yes. BB3. BB3 to. Okay, right. Yeah, this yeah, you can see that this is a very skewed 94% we are taking this, and is okay. So here also 94% we are taking. Okay. You can see that some edges are not labeled. Are we missing any information? Yeah.
don't know what is the percentage of the
Mm-hmm. Right, excellent. Yeah, it's 94%, so it's 6%, right? So there is no loss of information. Okay. So okay, so what do we do in global instruction scheduling? I'll talk about trace scheduling. Okay. So we will. So first we will identify a frequently executed path. Okay. So here you can guess that this path is very likely frequently executed, right? From BB0 we are very likely to go to BB3, and from BB3 we are very likely to go to BB4, right? So this is a sequence of frequently executed nodes. The control flows from one node to the other in that sequence, very likely. Okay, so let's call this sequence a trace. Okay, and what do? We place these basic blocks sequentially. Means can you guess what I mean by placing basic blocks sequentially? Excellent. Yes. Yes, we are trying to place this basic block right after next this thing, right? Why do we want to do that? Excellent. Yes. Yes, if we place these sequentially, right, then we are unlikely to take a branch to some other basic block, and thereby we can reduce the likelihood of branch penalty. Okay, so that's why we want to place the basic blocks in that sequence. Okay, in that sequence. Okay, by doing that we reduce the branch penalty. So two things that we saw, one is high latency instructions, second is branch penalty. So one of them we already tackled by doing this, right? And what we do next is we schedule the instructions treating the sequence as a single basic block. Okay, we try to schedule in this instructions in BB0, BB3, BB4, like that. Okay, so that's all. The conceptually it's all that. So okay, so now we will define some terminologies. Okay, side entry. What is a side entry in a trace? So BB0, BB3, BB4. This is a trace, right? Well, here we call BB3 as a side entry. Can you guess why we call it as a side entry? Right, control, see, this is the beginning of the trace and this is the end of the trace. Okay, start of the trace and end of the trace. And side entry means control can flow in between the trace. This is different from basic block where control cannot flow in between, right? So yeah, so this is a side entry. And can you give an example of side exit in this trace BB0, BB3, BB4? What is a side exit? Yes. Side. This is this edge represents a side exit, right? So that means you can even though BB4 is the end exit of a trace, end point of a trace, control can leave the trace in between. This is different from basic block where control flow can leave only at the end, right? So this is actually the branch instruction that takes control out of BB3 is a side exit. That's a detail. Okay, so side entry is a non-entry branch target within a trace. Side entry means the beginning of the instruction at the beginning of this basic block. That is the side entry, and side exit is the branch instruction that takes control out of this trace. Okay. Yes. Yes.
We have defined the basic block to be one entry, one or multiple exits.
No, one entry, one exit.
One entry, one exit.
I mean, okay. Okay, go ahead. Yeah.
So then, how can we have the side entries?
Yes, this is not. That's why it's not a basic block. It's a trace. Trace is a sequence of basic blocks. Okay, it's not a single basic block. Okay. So side entry is a non-entry branch target instruction within a trace. That's the starting of the first instruction in BB3 is a side entry, and the last instruction in BB3 is a side exit. Okay. Okay. So side entry is the BB3 entry instruction, and side exit is BB3's branch instruction to BB31. Okay. Okay. So but these side entries and side exits lead to some interesting, situations. Okay. While moving instructions across side entries and side exits, we need to be careful. Okay. Assume that this is a control. This is a part of a control flow graph. Okay. Start is the start node, and we have this one, right? Okay. Let's assume that they are all single. Let's assume that. They are all we will consider as single instruction as a basic block. Okay. We can even though we traditionally define a basic block to be a maximal sequence of instructions where a single entry and a single exit, right? But for we can also consider single instruction as a basic block for this example. Okay. So, and do you have any concerns with that, by the way?
Lots of basic blocks to process.
Pardon me?
Lots of basic blocks to process.
Oh, okay. Yeah, that's. I mean, at a conceptually, do you have any concern? See, we can always consider a single instruction as a basic block. I mean, conceptually, because the that is the control flow enters that instruction and leaves that instruction. So conceptually we can consider. Okay, so I will although it this will make the understanding easy. That's why I'm making this case. Okay, so okay. Let's also assume that data dependencies do not restrict movement. That is, they are all independent. These edges only define control flow edges. Okay, control flow means after I1, I2 is placed in this code. Okay, after I2, I3 is placed like that. Okay, they are all. Let's say assume that there is no data dependencies among these. Okay, now. Let's say we want to move I5 between I3 and I2. See, let's say we want to move I5 between I1 and I2. Let's say we want to move this. Let's say that Let's say that I1 is a high latency instruction, and we want to move I5 before I2. Okay. Oh, okay. Can we do some things like this? Like, can we move I5? See, can we bring I5 here directly?
Provided there is no dependency,
Huh?
provided it's an independent block.
Yeah. Okay. Yeah. Okay. Yeah. Let's say. Let's say that. Yes. Let's say that I5 is independent of I2, I3, I4. Okay. Let's say that moving I5 doesn't break any data dependence. Moving I5 between I1 and I2 doesn't break any data dependence. That is, I5 is independent of I2, I3, and I4. Can we simply move it like this?
We enter from 16, then
If we enter from I6, okay.
yeah, sorry, from I6, then we'll be missing that I5 computation.
Right. Let's say if I5 produces some value and that is used somewhere later, right? So yeah, so this is not correct, right? So that's why we have to be careful before. Is this correct? We moved I5 here, okay, but you said your name?
Keith,
Yeah, Heath, Kate, okay. So Kate said, right. So I5 and I2, right. So we have moved I5 and we have a copy of I5. Are you okay now, Kate?
should be fine.
Okay, yeah. So we need to make sure that we insert a copy of the. So what we are doing, we are trying to move an instruction above a side entry, right? So if we are moving an instruction above a side entry, we need to make sure that we move it in the other incoming edges of the side entry as well, so that this computation is not missed when we take this path, right? Okay. Okay, so we saw moving an instruction above a side entry, right? So let's see. We want to move I1 after I4. Okay, that's I1 we want to move after I4, that is below I3. I3 is a, yes, yeah, join is a good term, but in terms of trace, what is it? We gave new side entry, right? Yes, we want to move an instruction below a side entry. Can someone volunteer? Can you draw, or can you tell me? Okay, can you tell me how to do it? Anyone wants to volunteer? Yeah, I mean, there's nothing. I mean, it's just a puzzle, and don't we feel shy of making mistakes. I have made a lot of mistakes, very costly mistakes. Anyone? Come. Your name? Huh? Arnav. Yeah, please, Arnav. See, we want to move I1 after I4. Right. Okay. I3. What about I6? 6, right? I I I2, I3. Why is that? Why do we have? So why did we replicate these?
Because on that path I1 is not executed.
Because on okay, because on this path I1 is not executed. Why does it? What's the big deal? Why see, we are not, see there we didn't have a result. That's a concern, right? What's the big deal in executing something as an extra instruction in an off trace path? What's the big deal?
It will change the program. If the programmer looked at
It will okay, yeah. Can you give me a stronger motivation?
so professor told us that it could be an exception also.
Okay, right. So, which professor? I mean, did you learn it in this? Oh, okay. Yeah, that's nice. Excellent. Yes. So, let's say, right? Let's say this I1, right? I1 is like x by 0. Okay. If I1 was x by 0, right, then what will happen if we do this? We'll take an exception here, right? The program may crash, right? And what's the problem? Anyway, I1 instead of crashing here, we are crashing here. What's the big deal?
Crashing on both paths.
Right, right. So we are penalizing the. I mean, if the see, a trace doesn't necessarily mean the program always follows that path. Okay, it's very likely that that path is taken, but there is also a chance that path may not be taken. Right. So if we take this path, right, I6, I3, I4, I5, then if we take this path, right, I6, I3, I4, then I1, then the program crashes. That's not correct, right? So that's why we need to. That's why Arnav did it like that. Excellent, Arnav. Yeah. Where did you learn this? In which session did you learn this? Okay. PRE. Okay. Right. Yeah. So it's so we should be careful in moving instructions below a side entry, right? So so what are we doing here? What are we? Okay. So the advantage is that I mean, we are able to hide the latency of I2 by bringing some unrelated computation, right? But what's the disadvantage of this? We are creating. What is the disadvantage? Yes, copy. We are creating copies of instructions, right? So that's a concern. I mean, in many cases it may not be a concern, but in embedded applications, I mean, it may be a concern. Code size is a real concern in some domains. For instance, our customers, right, in industry, they are very particular about code size increase. They cannot tolerate code size increase. So it's not always good to create copies. Okay, but in some cases, if the application is domain is such that it can tolerate code size increase, then they are free to do it, right? Okay, so okay, now let's take this trace b1, b2, b3. Okay, what is the side exit here? Huh? Yes, the branch instruction that that branches to yes, b2 to b4 branch instruction is a side exit. So we are trying to move this computation below a side exit. Can we move x equals y plus z below this b2 b4 below the side exit? Like for instance, this is this correct? Right. Right. So here we won't get the correct value of, if we take an off trace path, we won't get the correct value of x, right? So this is not correct. So okay, do you want to volunteer fix this? Anyone wants to volunteer? Can you fix this? Can you fix this code? Don't feel shy, please. You will never forget this. This concept you will never forget if you come and do it on the board. In your life, you will never forget. So it's okay to forget, is it? It's not difficult. Nobody wants to come. Yes. I'll just a minute. Yeah, someone. Yes. Okay. Okay. Yes, that's good. So, thank you. Yeah. So yeah, I'm sorry I forgot your name. Aditya. Yeah, Aditya fixed it, right? So yes, and as you said, your name? Huh? Shreyas. Yes, Shreyas was suggesting we can create a copy on the off trace path, right? Does anyone have any concern? No. Okay. Right. So okay. Okay. So now we saw code movement below a side exit, right? Let's see what happens when we try to move code. Okay, now can some okay, let's this is a trace here. Okay, b1, b2, b3 is the trace. Okay, what is a side exit here? Yes, b1 to b3, right? Because this is a trace and we are not following the trace, we are taking a path outside of the trace. That's why it's a this is a side exit. Okay, can we move this computation above the side exit? Huh? Okay. No, we can move, right? Okay. So,
If we move up, maybe the Z1 or Z2 value which is already present in V1 can affect value in V3.
right, assume that the only use of Z1 is here. So, okay. So this one is, we can do this, right? We can move this here, right? I think Arnav may have a concern.
We have to divide V1 into two parts
Mm-hmm.
because V1 to V3 does not perform Z1 to Z.
Right. Yeah, we can do that. Yeah, right. So again, see, we may think that hey, we are executing an instruction in the extra instruction on the off trace path, right? What's the big deal? But y could be 0, right? So there we must be careful when doing redundant computation even in the off trace path, because that redundant computation should never cause an exception, right? So that's why we need to be careful. So yes. So right. So if we saw what are the, I mean, we covered 4 cases: moving an instruction above or below, side entry or side exit. We covered all 4 cases, right? So okay, someone said that I mean, someone had other concerns, right? Moving Z1 here. Shreyas, you had a concern, right? What? Can you
I
repeat?
asked whether what if V1 has some different value of Z and V2 gets some different value of Z.
Yes. Yeah. So yeah, that's a very valid concern. Which which data flow analysis will help us figure out that it's okay? Huh? Yes, SSA. I mean, if it's in SSA form, then okay. Let's assume the program is not in SSA form.
Live variable let us know if this has any dependency.
We live variables means, can you be a bit more
Maybe we
precise?
can check liveness. Maybe we can do liveness analysis of a particular variable at that particular
Which point?
V1. If the variable isn't live between V1 and V2, then V2 sure has a newer value as compared to V1.
Right. So okay. So yeah, another point I wanted to make is, so you can already see that the concepts that you learned in other lectures, right? Like SSA, liveness, data flow analysis, so they're all applicable here, right? Yeah, Shreyas.
That's what I asked. Like, what if other, I mean, V1 branch had some different values, and that the value which was present in Z1 and V2 got propagated to V3, which it shouldn't get, right?
Right. Yeah. So okay. Okay. This brings us the question: is Z1 live at B1?
Not correct.
Huh?
Not correct.
No. No. Yes.
No.
No. Okay. Yeah. Can you say that before without examining the instructions in B3? We can't say, right? So we don't know if Z1 was here. B3 could be like Z3 equal to Z1 plus Z4, right? In that case, Z1 is live, right? So we cannot right, we cannot move because it will, I mean, so we cannot move here if Z1 was live on the off trace path, right? This is the off trace path, right? So Okay, so we saw some code duplications across side entries and side exit, right? Which among these, which one do you think is the most, which is the most complex thing? Is movement across side entries complex, or is movement across side exit complex? I will help you with this, right? So okay, for movement across side exit, right? In the worst case, what do? We create, if we want to move this, right, we create a copy of this in the worst case, in the off trace path, right? This is for across side exit. Here, right, what do? If we want to move I1, right, what are we doing here? What we are creating copies of I3 and I4, right, on the off trace path, right? And what are we doing here? We want to move I5 between I1 and I2, right? Here what we are doing, we are creating a copy of the instruction that we want to move in the off trace path, right? Okay, among these, so here if we want to move I5, we are creating a copy of I5 in the off trace path. Okay, here if we want to move I1 below an off trace side entry, what we are doing, we are creating, see, we want to move I1 below the side entry, but what are we doing? We are creating copies of I3 and I4 in the off trace path, right? And here we are, if we want to move this computation, we are creating a copy of the same computation in the off trace. Among these, which is more complex? This one, or this one, or this one? Which is the most complex among these? This one, right? These side entries, right? They create, they are more complex to deal with, because we are not, we have to create copies of unrelated instructions, right, on the off trace path, right? It's not sufficient if we just care about I1. We need to care about other instructions as well in the off trace. We need to create copies of unrelated computations in off trace path, right? So side entries, dealing with side entries are a bit complex, right? So I'm just noting this movement code motion across side entries is more complex if we want to certainly do it. Okay, so that's why instead of traces which have both side entries and side exits, researchers came up with what are structures called super blocks. Okay, super blocks is a in a super block there will be a single entry point, but there can be multiple exit points, right? So okay, so okay, which is a trace here? BB0, BB3, BB4. So we have already placed linearized these, right? Why did we do such linearization? Right. We don't have, because we don't want to take branches, right? So most likely the control will flow from here like this without branching elsewhere. That's why we linearize this trace, right? Okay. And now, but the thing is, what is the side entry here? This is the trace. Okay, this is the entry, this is the exit. Which is the side entry? Yes, BB3 is a side entry because control flank can happen. I mean, in between this trace to BB3, right? Okay, what is the side exit here? BB3, right?
And BB0 as well.
Yes, BB0 is also a side exit, right? Yeah, so I'm missing it. Side exit, it's not just BB3, it's also BB0, right? Uh, okay, so I made this mistake. I'm not shy. Okay, so okay, so how do we now we have a trace with side entries, right? How do can anyone do any of you want to attempt creating a super block out of this trace? The goal is we should not have side entries. We don't want this these edges bb1 bb2. Does anyone want to volunteer? This is not I mean this is not a straightforward thing, so I'll give you a hint. You can create copies of basic blocks. And does anyone want to volunteer? Want to volunteer? Come. Where is the? It's here. Your name?
Jayashri.
Huh?
Jayashri.
Jayashree. Hi Jayashree. Yes, this is the trace, right?
Just
BB2.
copy out of this, so we don't have an entry with this exit.
Okay. Okay. Yeah, excellent, Jayashree. There's just one thing that we are missing here. How many edges are? I mean, what are the outgoing edges from BB3?
Okay.
Yes. Right. I
I mean,
think.
that exit is covered here, so this won't be necessary.
Okay.
Because a copy of this is made here.
Oh, okay, but from BB3, right? Let's say we are taking this BB0, BB3 and BB31.
Okay, BB0, BB1.
No, I'm not talking about that path. This is a legal path, right? BB0, BB3 and BB31.
Yeah, so this edge is valid then.
Yes, yes, yes. Excellent, Jayashree. Thank you. I think it's the same BB1 and BB3 copy, and right, BB3 one. They are isomorphic, right? Yes, no.
Copy of BB4 is a copy of BB4.
BB4.
And BB3 is copy.
Okay, right.
Why do we need a copy of BB4?
Yes, because let's take this off trace path BB0, BB1, BB3, BB4, BB0, BB1, BB3 and BB4. This path is not there, right? Okay. Yeah. So what we are doing is yes, yes.
Now, isn't the BB3 one having two copies of BB3, which both, I mean, two copies of BB3
Pardon me, Shreyas. BB31.
has two copies of BB3, right? Both are assigned from two different.
Yes, yes.
So we need a kind of a find function or something.
Okay, this is say okay. Just to clarify, the now the okay during register, I mean instruction scheduling, right? We don't the code will not be in SSA form. So okay. I will tell you, I'll give you the details shortly, but the code will not be in SSA form. Okay. So is everyone convinced that this is all right, or do you have any concern? So you can okay. Do you have any concern with this compared to this? I'm not talking about correctness. Do you have any other concern? For instance, you are optimizing code. I mean, your customer is an embedded systems application guy people.
Here the branching is increased.
Yes, branching is increased, and yes, we are replicating copies of BB3 and BB4, right? Right? So you can see that code size increase can happen when we create super blocks out of traces, right? Now, okay, now are we convinced that this is a super block and not a trace? Why is this not a trace? Yes, there is no side entry. The control, I mean, can start only from BB0. But other side exits, what are they? This is a side exit, and yes, this is a side exit of trace, right? So yeah. So yes, super block scheduling simplifies instruction scheduling, but at the cost of increased code size, right? So this is called tail duplication. Okay, tail is from the first side entry we are actually duplicating it. That's called tail duplicating. Okay, this can sometimes lead to significant code size increases. Okay, right? Okay, now we saw this. I mean, we saw. We didn't really say how we will form a trace, right? We just said that hey, the most frequently, I mean, a sequence of frequently executed nodes is a trace. That's all we said, right? But actually, there is a well-defined algorithm for forming trace. Okay, this I will not. I'm not going to into the details of it, but you will get a chance to work on it in the next session. Okay, essentially, what we are doing is. We will consider nodes inside a loop. Okay, and what we do is we will pick the basic block that is most that has a very highest execution count. Okay, and we will add it to the trace. Okay, and then we will try to keep extending the trace by following its most frequently executed successors. Okay, for instance, let's say let's say that these three are executed like 94, 94, 94 times. Okay, so what we do, and these three are inside a loop. Let's assume what we'll do, we'll pick BB0. We will end up with the same trace even if we pick BB3 or BB4. Okay, don't worry about it. But let's say for the sake of simplicity, we pick BB0. Okay, and we try to extend the trace forward by examining its most frequently executed successor. What is the most frequently? What are the successors of BB0? BB1 and BB3, right? Which is the most frequently executed successor? BB3, right? Okay. Now add BB3 to the trace. Okay. Then what do we do? Again, from BB3, which is the most frequently executed? BB4, right? Then BB4 is this is a trace. From BB4, there is no successor, right? So we stop here, and then we'll try to go the trace backwards. Okay, so is there any predecessor of very frequently executed predecessor of BB4? BB3, but BB3 is already in the trace, so we don't have to do anything. So its trace is a set. I mean, so it's already there, so we don't have to. So even if we start with BB4, right? What we'll do, we will try to find the most frequently executed successor. There is none. So what we'll do, we'll try to extend it backwards. We'll try to find, I mean, the predecessor, most frequently executed predecessor, BB3, and then we will end up with the same trace even otherwise. Okay, but okay, so like for instance, we can have some when choosing the successor or predecessor, right? We can have some thresholds, like say for instance 85%, the successor should be taken 85% of the time. We can have these thresholds, and these are not very written on stone. It's we who choose this number. Okay, so depending on the application behavior, we can choose these thresholds. We can play around with these thresholds. Okay, so so now what did we see? We saw why we needed scheduling beyond basic blocks, right? And what are traces, super blocks, and how to schedule, how to move instructions above and below side entries, right? So okay, and what is the advantage? What is the advantage of super block scheduling? It's less complex than trace scheduling, right? Because for trace scheduling, if you want to move some instructions, we have to make copies of unrelated instructions. It simplifies instruction scheduling. Okay, and what is the concern with super block scheduling? Code size. increase can happen, right? Even with the trace scheduling, code size increase can happen because we need to duplicate instructions, right? Even for trace scheduling, we needed to duplicate instructions, right? Unrelated instructions as well, right? So so you are if you are developing if you are writing a scheduler for an embedded customer, right? Our customers may say that we cannot tolerate any code size increase at all. That's what our customers did. Okay, they cannot tolerate code size increase. Okay, so and secondly, embedded processors may not have some sophisticated hardware support for moving loads and stores across basic blocks. Okay, we will see that in the tutorial why. Okay, so but the idea is the same. You cannot, why we cannot move loads to different basic blocks. See, for instance, right? Suppose this was a load instruction. It is where we are loading reading from like it's star x. In C we have indirection, right? Star x, where star x is a pointer and we are doing y equal to star x. Let's say we have a computation. Can we move it here? Right. So so loads are also, loads or stores are also concerns, right? We shouldn't load from illegal pointer, and more importantly, we shouldn't write even to legal pointers. We shouldn't overwrite. See, the cost of what's the difference between moving a load and moving a store? Why is moving store more concerning?
Because you had data recording some other value in variable which could already be storing some value.
Right, we are overwriting value, right? And if we are taking the other path, it's the same as someone said liveness, right? What if the value you shares you said, right? It's the same, right? We shouldn't destroy any live value, right? We shouldn't destroy any live register. We shouldn't destroy any live memory location also, right? That's the same thing. So it's not for stores. It's not just sufficient for us to guarantee that the pointer is pointing to a valid location. Even if it points to a valid location, we should be very cautious about moving stores, because if the location was read in an off trace path, then it will be reading a wrong value, wrong result, right? So we should be careful about moving loads and stores, right? Okay, so this okay, some processors, right, they have special instructions to deal with this. Marker. Okay, thank you. So did you learn about speculation in load speculation in computer architecture? Okay. Yeah, prefetching is there, right? Yeah, speculation is kind of a prefetch. Okay. Okay. For instance, right? If PTR not equal to null, right? Then true, then false, right? Right. Okay, So right, this is the false. Can you guys see this? Okay, thanks. Yeah, so right, we cannot. Can we move this here? Yes, no, no, right? Why?
It may be a null, so it will be referencing null.
Right. So we cannot move this here, okay? But in some cases, right, if the hardware provides facility to, so in some architectures, right, what we can, okay, instead of y equal to star ptr, I will write load r1 ptr, okay, that's the same, okay. So what we can do is, in some processors, right, they may have a special version of load instruction called a speculative load instruction, okay. What we will do is LDS load speculative R1 PTR, okay, and then we can have if PTR not equal to null, okay. This is a special version of load called a speculative load. Even if PTR is null, right, okay, the exception will, the hardware will record that there is an exception, okay, but it won't take the exception, okay. What we have to do is, what the compiler has to do is, it has to insert a what will do is, it will insert a verifying load R1 PTR, okay. Okay, so exceptions will be taken only if we, if we hit a load verifying load, and we take and this is a null pointer, okay. So this load will not raise an exception, and only this one will raise an exception, okay. So this is called a speculative load, okay. Or in some cases, yeah, but this kind of feature may not be available in embedded applications. So that's why we cannot simply move loads and stores across basic blocks, okay. And okay, so what we did is, we terminated traces immediately before side entries, okay. So our super blocks were very small, okay. Instead of tail duplication, instead of replicating basic blocks, we terminated super blocks before side entries, okay. And also if you do that, there is no need for tail duplication, and there is no need for fix-up code insertion, that is creating copies of unrelated instructions that we saw, right. So but what is the disadvantage if we do this? The advantage is that we don't we don't have to pay the price of code size increase, right. What's the disadvantage if we terminate super blocks immediately before side entries?
Very small.
Excellent, yes. The main goal for going for superblock scheduling is hoping to have a large window of instructions so that we can rearrange them. But if a superblock sizes are very small, then that's it may not be useful, right? Okay. yeah. Yeah, but still, right? If your application is such that this doesn't create, I mean, this doesn't become too much of a bottleneck, you can surprisingly it worked even with this restriction, right? In our if in our application domain, it didn't hurt. I mean, Superblock scheduling was still useful in spite of this limitation. Okay, and the second thing is downward code motion across side exits is prohibited. If we do that, right, if we prevent this motion, right, if we prevent movement of x equals y plus z below this b2 b4, right, then we don't have to, I mean, we don't have to duplicate, right? Okay. Again, this will limit the code motion opportunities. Okay, but still it may be fine in some cases. Okay, and also we didn't allow load store movement across branches. Okay, what should we, I mean, if we want to relax this restriction, what should we do? If we want to move at least loads, say if condition then y equal to star x. Okay, this is a load. Okay, we are reading from this x location. If we want to move this, what should we do? I mean, what should we prove if we want to move this here? Yes, excellent. X points to a valid memory location, right? So yes, if you want to relax this restriction, then we have to show that they won't generate an exception when the I mean, when the side exit is taken. Okay, they shouldn't generate an exception. Okay, even when this is taken. Okay, if the obviously if the condition is if x not equal to null, okay, then obviously this is not a, I mean, moving this here won't be a valid code motion, valid movement. But if we can show that at this point, right, at this program point and this basic block, x points to a valid location, right, then we can move this. Right. So yeah, so I think we can take a break now. Okay, we'll come back after the break. Fine. Okay. Post this break, what we'll do is we'll see how we implemented. We'll give an idea of how this was implemented in LLVM. Okay, and then we'll share the results, and then we will have a hands-on session where you will work on problem. Okay, thank you. Yeah, because see the, I'm sorry.